Hey everyone, welcome back to Mind and Maths with Amina. In today's lesson, we are going to study stability and determinacy in new Keynesian models. This is important because modern macroeconomic models are actually forward looking, and forward looking systems can easily generate multiple equilibria, explosive paths, or sunspot driven outcomes unless the policy rule pins down properly. Our key tools today will be the BK conditions, the eigenvalue analysis, how stability changes under different policy parameters, and what indeterminacy means and why it matters for policy. But before we begin, I would like to emphasize the fact that we are going to be working with the canonical cashless new Keynesian model. In the cashless model, basically the LM curve is completely dropped, okay, and there is no money demand equation. Money does not basically appear anywhere in the equilibrium conditions. Therefore, determinacy comes purely from the Taylor rule. This is the model that we've been working with. We've had the three equations. We had the IS curve, the Phillips curve, and the Taylor rule was provided to us. So that has been the model that we worked with. We did not have four equations, okay? We would have ended up actually with four equations if we were working with money and utility or a cash and advance model. In that, money would appear as the fourth equation, and we would then we would have to reconcile money supply with the Taylor rule. But in the canonical new Keynesian model, money basically plays no no role in the equilibrium selection. Anyhow, moving forward, we derived previously the IS and the Phillips curve, and the Taylor rule is basically just provided because it's just a policy rule. Remember, all these are log linearized. Okay, as you can see over here, the IS curve is forward looking because it contains an expected future output. The Phillips curve actually is also forward looking because current inflation depends on expected future inflation. Taylor rule is just a policy rule. It shows that if inflation rises above the target, then you should increase the interest rate. And if output goes above its target, that you should increase the interest rate. The real interest here is basically shown as AR1 shock, and this is predetermined because today's value depends on the lagged value of itself. So if today's value depends on the past, then we have a predetermined state variable. So I'll repeat what a jump variable is and what a predetermined variable is. Remember, a variable is a jump variable if its equation contains expected future values. And over here we can see xt and pi t are going to be the jump variable. The reason why this is important to establish is because in the BK conditions, the number of unstable roots has to be equals to the number of jump variables. So it's very important that you are able to identify the number of jump variables. Okay, what about the predetermined variables? Okay, so a variable is predetermined if today's value depends or basically is pinned down by the past, not by expectations. So you can see over here Rn is predetermined. Why is it important to establish the predetermined state? Because the number of stable roots has to equal to the number of predetermined states. Okay. Now let's talk about the reduced system. Remember, if I make these three equations and into a 3x3 system, it's going to be a bit more difficult for me to work with. So it's always easy to have a 2x2 system. So therefore, we want to substitute the Taylor rule into the IS curve to obtain equation number 1. This is what I've done here, that the Taylor rule got substituted in, and we got equation number 1. Equation number 2 is just the Phillips curve itself. Okay, then I wanted to make the expected value of these variables into the subject, and that's pretty easy to do. You just take the inverse of the coefficient matrix and you multiply it through, and then you'll get a system that is of this form. Now, the main important matrix that you have to look at is matrix A. This is our key object, and the BK conditions apply only to matrix A. So what is the BK conditions? Basically, the theorem tells us that a unique bounded rational expectations equilibrium should exist. Basically, it does exist if and only if the number of eigenvalues of A outside the unit circle, as in unstable roots, equals the number of jump variables. So we have to be able to establish the jump variables, and we count them. If there are two jump variables, then we have to have two eigenvalues outside the unit circle. That means two unstable roots. If we were working with the 3x3 system, then obviously it's a 3x3 matrix, then you have to get three eigenvalues. So two of them will have to be unstable and one of them will have to be stable in order to get a straddle path equilibrium. Similarly, when we actually reduced it into a 2x2 system, then you're going to end up with two eigenvalues, right? So both of these eigenvalues have to be unstable in order for you to end up with a saddle path. So basically, I think all of you already know what a saddle path is, but I'll still explain it. Basically, a saddle path solution exists when there are infinitely many explosive paths, but only one path is bounded. So expectations, jump instantly to put the economy on that path. So if the number of unstable roots equals the number of jump variables, the jump can exactly cancel the unstable directions. So let me just give a rough kind of, suppose this is the diagram and there's this is the saddle path. So if there's any kind of jump, suppose from there the economy was here, so the economy would jump exactly onto the saddle path and then converge to the steady state. So this only happens when the number of unstable eigenvalues equals to the number of jump variables. Remember that in the ISLM model, which we were doing previously, and I made two videos on, the saddle path equilibrium when it comes to difference equations and differential equations. Remember, we had output and interest rate on the vertical axis. Output over here is a predetermined state because it actually can never move quickly. However, the interest rate is a jump variable because the government has the authority to change it. Okay, so if this was one jump variable, that means for a saddle path we required one unstable root, and we required one stable root. This is why, remember that when we ended up with the final answer, we would, in order to find the saddle path equation, we would make the coefficient next to the unstable root inoperative, and that would give us the saddle path equation. So the reason why one had to be unstable and one had to be stable was because we had one jump variable and one predetermined variable. Okay. So coming back to the new Keynesian model, you can either find these notes in the description of the playlist, Macroeconomic Analysis. So I'm just going to skip all the theory that's been explained because I've explained that in any case with words. So I would rather actually jump onto a question because that is always better in understanding a concept. Okay. Suppose we have these three equations, the IS, the Phillips curve, and the Taylor rule. In order to get a 2x2 system, you substitute 3 into 1, and you get the first equation. And the second equation, we have xt, and I want to remove that. Therefore, I will substitute equation 1 into equation 2. when I do that, I will get a equation of the expected value of these variables in terms of the actual value. So when we do that, I'm just going to convert this into a matrix form. See, the coefficients are 1, 1, 1, 1.5. So 1, 1, 1, 1.5. And the expected value of these variables, then we have a 1, 3, a 0, and a 4. So 1, 3, 0, 4. Then I take the inverse of this matrix and I multiply it through, and this is the matrix A that I end up with. So this is my main matrix of concern, and I want to find the eigenvalues of this matrix. For that, I have to solve the characteristic equation, which is basically just the solution of this, which is the determinant of A minus lambda identity. When we solve this, unfortunately, annoyingly enough, for this question, I ended up with what you call them, complex root, right? So I didn't end up with like two positive roots here quite easily. I ended up with imaginary root, and this is the imaginary root and this is the real root. So when you end up with complex roots, all you have to remember is that you need to check the modulus of that complex root, which is basically just the radius. So if the modulus is less than 1, then you have two stable roots, and that cannot give you a what do you call it, that doesn't give you a saddle path, right? If you have the modulus greater than 1, then you get two unstable roots, and then yes, you do get a saddle path. If it's equals to 1, then then there's nothing you can say about it. It's just indeterminacy. Okay, so over here the real root was 5 over 2. The square of that was 25 over 4. The imaginary root was an under root 7 over 2, the square of which is 7 over 4. So we just use the Pythagoras theorem and we find the length of the radius, which is basically an under root of 8, which yes, it is greater than a 1. So yeah, both the roots are unstable as required, so the BK conditions hold, and therefore we can say that a saddle path equilibrium does exist. Okay, so I hope this was I meant for this to be a short video. So basically the key takeaway is that the entire determinacy question in new Keynesian models boils down to whether monetary policy creates enough instability in a forward-looking system so that expectations jump onto a unique stable path. This is why the Taylor principle matters. So if the professor gives a question like this, all you need to remember is that the main assumption is a cashless limit, which means we don't have a fourth equilibrium for money market equilibrium equation. There's just going to be the IS curve, the Phillips curve, and the Taylor rule. You want to put the Taylor rule into the IS curve to get a 2x2 system, and then you want to express the expected value of the jump variables in terms of the variables themselves and find the matrix A. Once you found the matrix A, you have to see if the BK conditions apply, and for that you will have to find the eigenvalues. If you have two jump variables, then what you are looking for is two eigen values that exceed 1. If you end up with, suppose you have one jump variable and one predetermined variable, then you're searching for only one eigen vector which is unstable, and so on. So that's what I wanted to do for today, and yeah, that's it. So I will see you in the next one. Take care.